This is our Excel Bootcamp 4, following the first 3. And the purpose of this one is what we would describe as capstone. In other words, we're going to bring together many of the tools and skills that we have covered in the first 3 boot camps and apply them to 2 modeling and simulation problems that are somewhat more complicated. The purpose here is to provide you with guidance about how you might approach a complex modeling problem. And although these models are not perhaps as complicated as what one would find in industry, they do approach that, and they're definitely more so than what we have seen in the problems that we addressed in Bootcamp 3. Also, I will mention that it is an alternative for modeling like we're going to address here, that one might use professional software such as Aspen Plus or HYSYS to address these scenarios. But there's also a couple of cases here where that's really not feasible. Number one is you may find yourself in a situation professionally where you do not have access to the simulation software packages that are provided at the university. And the other is that many times actual industrial applications do not precisely fit the tools provided or modules provided by the professional software. And in the case of a software like Aspen Plus, they provide the capability for you to add custom modules to address particular situations, but those modules have to be written in the Fortran language and may present complexity that you would rather face using other tools, such as we have addressed in the boot camps. Here, Excel and VBA, and in the others, MATLAB or the Python language. So we're going to proceed here and look at, in the first part of this boot camp, the modeling of a classical process, which is a packed bed plug flow reactor operating at high pressure to produce ammonia. So let's move on and take a look at the model that we will compose in order to address this. Once we have the model organized, and in many cases that is a considerable part of the effort, once we have the model organized and the basic data collected, then we will show you how we approach solving the model using Excel and VBA. So we're looking at a plug flow packed bed reactor, and it turns out that the reaction kinetics here are relatively simple. It's for the combination of nitrogen and hydrogen to produce ammonia, but the reaction has a forward path and a reverse path, and these are described here in terms of partial pressures, because this is a gas phase reaction where we have a forward rate of reaction where the rate parameter is temperature dependent and is provided by the Arrhenius expression with these parameters for the pre-exponential factor or frequency factor and the activation energy. And we have a similar expression for the reverse path, where it is a function of the partial pressure of ammonia. And again, with similar description in terms of Arrhenius description and So that describes the reaction kinetics. And then we want to picture the reactor that we're dealing with. This is a reactor that typically has an iron catalyst in small pellets, and it is, in this case, we're describing it in a cylindrical configuration. This is an adiabatic reactor. In our next example, we'll be dealing with a reactor with heat exchange that has many, many small tubes, but here it's just an adiabatic packed bed. And as shown here, we're feeding nitrogen and hydrogen. When we get to the actual model, we will have a couple of inert gases that enter into the reactor and pass through without participating in the chemical reaction, but we're only dealing with the components here that react. And as we pass through this cylindrical packed bed space of a given diameter and length, some of the nitrogen and hydrogen is converted to ammonia, but not all, and we have a significant amount that passes through unreacted. And that's why in ammonia processes there is a subsequent separation or condensation of the ammonia and then a recycle of the unreacted nitrogen and hydrogen. So we create a fairly simple differential mole balance here in terms of the molar flow of nitrogen. And that is described by our forward rate. That's why it's minus, because it's consuming the nitrogen, and the reverse rate, which is producing nitrogen from ammonia. And then the volume here is in terms of the empty volume of the cylindrical space. So we apply the void fraction, which then represents the amount of space available for the gas to flow through the bed. And so we apply the void fraction to that equation. And then there's some geometric notes down here in terms of the differential volume, in terms of a cross-sectional area times a differential of length, and then the cross-sectional area and the total volume of the reactor given here. It turns out that that's the only one we need to track, because if we have feed conditions, we can determine the flow of the hydrogen and of the ammonia by the amount of nitrogen that has been consumed and in this case, the feed hydrogen, using the stoichiometric coefficients of the reaction. So we can determine these two flows algebraically once we know this flow by solving the differential equation. Okay? So let's move on and talk about the energy balance here. This is an adiabatic reaction, all right? And it is an exothermic reaction. And so a general enthalpy balance would have the change, it would have energy conservation. So the sum of the enthalpy flows, all right, would differential with respect to volume would be equal to zero. Now, if we are able to use a constant heat capacity approximation, then we can reduce this to a differential equation in temperature, where we have the energy generated by reaction here, and our flows times heat capacities can be brought over from the left-hand side and have as a denominator over here. And we note that the heat of reaction may well be a function of both temperature and pressure. And it's important to note the pressure here because we're operating at high pressure. So when we're dealing with accounting for enthalpies at both temperature and pressure, we have the integral for the temperature effect involving the heat capacity, a function of temperature, integrating from a reference temperature up to a given temperature. And then we also have the pressure effect on enthalpy given by this thermodynamic expression integrated over pressure. And then we have an initial enthalpy that we account for at the reference conditions. So separating these two, we can take this term, and often we describe it in terms of a mean heat capacity, all right, times the temperature difference, all right? And the mean heat capacity is an integral of the heat capacity over the temperature range of interest here. And then the pressure effect on enthalpy can be more of a challenge to deal with. We can deal with it if we have an equation of state that we can work with analytically. We can work with actual data, or we can use something called the generalized Pitzer correlation, which you will see, all right? So then we move on and we say, well, what about pressure drop as we go through this packed bed? And the typical relationship that's used to predict this is the Ergun equation, which is denoted here in terms of nomenclature that is defined over on the right. And we have our void fraction against here. We have the diameter of the particle now, not the diameter of the bed. We have pressure difference over the bed, density of the gas, and we have the mass flux, which is defined as the mass flow rate over unit cross-section area of the empty bed. And because of conservation of mass, this is constant with the volume. And then on the right-hand side, we have similar terms. And we can use this as the basis for coming up with a differential form for the derivative of pressure with respect to volume, and that's this expression here, okay? So one challenge that we have to deal with here is coming up with the fluid viscosity, and we will address that a little bit later. So this would give us the opportunity to model the pressure drop, because if we are flowing gas at a high rate through a packed bed with relatively fine particles, we may have a significant pressure drop as we go through the bed. And in handling that, we have to know the fluid density, and the fluid density we can take as the average molecular weight over the specific volume. And in this case, we can get the specific volume from an equation of state which is appropriate for modeling these gases at high pressure. And a common one here is the Peng-Robinson equation of state, which is a cubic equation of state, which is denoted here, where you have mixture coefficients, A and B, all right, and then you have specific volume, gas law constant, and temperature and pressure. And so if we have the A and B coefficients and we are given conditions of temperature and pressure, we can solve this equation numerically for the specific volume, and then that goes in here to determine the density. And we have to figure out how to handle the mixture coefficients. I denote here that if we only use the ideal gas law, it would be very simple, but when we're operating at 150 atmospheres, the ideal gas law is off by as much as about 20%. So it's important to consider a more realistic equation of state. And then we move on and we talk about these mixture coefficients, and we're getting down into the details of modeling this. And the coefficients, Peng-Robinson coefficients for individual components, are given by these two expressions in terms of critical temperature and pressure. And here, this one in terms of the temperature and critical temperature. And then it uses a factor m sub I, which is given by this relationship and the omegas here is called the acentric factor for component I. And then we have whatever the mole fractions are that we're working with, and we can then come up with what are our mixture coefficients. And the way we get the mixture coefficient A is from a quadratic form, x transpose qx, where x are the mole fractions, and q represents this matrix here, which is computed using the individual A's from the components and a set of binary interaction factors, and these are denoted here in a off-diagonal matrix. And this is not really a matrix multiplication, it is an array multiplication of item by item, and that then gives us the Q matrix, which we can use to get the A coefficients. And then the B coefficients are handled quite simpler with the mole fractions, all right, and a vector of the individual component B's that are gotten from up here. So this sort of puts together everything that we need, and then it's useful to have a way of organizing this. And what we use, you've seen in the previous bootcamp, is we use something called an information flow diagram, which in this case, since we're dealing with a more complicated process, is more involved. And this one here is the one that we use for what we call the simplified model. And the simplified model is where we are assuming constant heat capacity and we're neglecting pressure drop through the reactor, all right? That gives us then a simplified model. And as we showed a couple slides ago, instead of a differential equation in terms of enthalpy, we have one in terms of temperature, and this is the expression that we used before, and here we have the constant heat capacities, all right? This, through solving this equation, gives us the temperature, and then we have our differential equation for flow of nitrogen, and that, when we solve that, it gives us the flow of nitrogen. These are the two stoichiometric relationships which give us our other flows, and we can combine those along with, in this case, argon and methane as our accompanying components that do not participate in the reaction. That gives us our total flow. And then with our total flow and the operating pressure, we can get the partial pressures of the three key components. And these go into the reaction rates, which then again allow us to specify the derivative. And then we need the temperature here in order to calculate the Arrhenius parameters. So this organizes the model for us. And now we want to take this and translate it over to an Excel spreadsheet and show you how we solve the model. So it's not practical at all to build this from scratch. So we're going to be opening a file here that is called Ammonia Simulation Simplified Model. And it looks like this. Now we will expand the zoom on this in a moment so you can see things more clearly. But essentially what we have across the top of the spreadsheet, if we have a lot of information which represents basic data and operating parameters. So we have our feed conditions here. We specify the void fraction, the reactor dimensions, particle diameters. Here are our kinetic parameters. Here we have coefficients in order to determine molar enthalpies, and then we have heat capacities which we've determined to be constant. So, and then if we go across, you'll see that we have more we have the Pitzer correlation for pressure correction of heat of reaction. This is the binary interaction matrix. Here, the omega sub i's, the Pitzer eccentric factor, and here are our critical temperature and pressure. So let us go to a little bigger zoom here. Take it up to 150 so we can see things clearly. So you'll find that most of these cells have names. Here it is feed N2. And in fact, if you use the drop-down list, you'll find that we've used names extensively in this particular simulation. So dP, diameter of the particle, is right there, and so forth and so on. Now, as we come down below, we get a block which is similar to the differential equation models that we solved in Bootcamp 3. And what we are doing here is we are using volume of the reactor as our independent variable, and we're using a pretty small integration steps of 0.001. And so if we go to the bottom here, we'll see that we are, to complete to the full volume of the reactor, we require 7,000 rows for this simulation. So it is more extensive. And then if we come back up to the top, what we've got for our first row is we've got our initialization row. So if we look at this one, this is just a pointer to the feed of nitrogen, which is above in the operating conditions. And that is the same for the hydrogen, the nitrogen, and then we have flows of argon, of the inerts, argon and methane, and those are molar flows, and those do not change as they go through the reactor. So then we come across, and we have partial pressures, all right? And the partial pressures have to do with taking our feed rate of nitrogen over the total feed, and then multiplying that by the feed pressure, which in this case will be constant. So we get partial pressures. Once we have partial pressures, we can calculate what the forward and the reverse reaction rate parameters are. And then we can calculate the reverse reaction, which in this case is 0 because there's no ammonia yet. And then we have the differential of nitrogen, flow of nitrogen with respect to volume, and that is given by the equation that we described. So beyond that, we look over here and we see the temperature, and here, this is the feed temperature here. Sorry about that. This is the feed temperature. And then we come across and we have the heat of reaction, and there what we do is we are, and I don't need this @ sign, but we use a user-defined function in VBA to calculate the heat of reaction according to the formulas on the slides, given the temperature and the pressure, okay? Then we have our energy balance, and our energy balance computes a derivative according to the formula that had the numerator divided by the sum of the flows times the heat capacities, and that we have to calculate the differential. And then down here we can compute a conversion as a parameter of interest. Now if I come back across, that is the initialization row. So what do we do in terms of the first operational row for nitrogen? Well, we've seen that before. That is just simply the Euler integration formula, where we take the previous value of flow of nitrogen, multiply it by the rate of change of nitrogen that we looked at way over to the right in the row above, times the difference in, or our step size, or difference in volume between this location and the one above. So that's how we get that. And then after that, these formulas here are just operational already above, so they can be copied down. And you can notice that the inerts are just constant. And then the total starts to change, and eventually the temperature starts to change. And we come over, look at this. And this, again, for the temperature, is the Euler method, where we take the temperature above times the rate of change of temperature versus volume times the difference, or delta, in volume. So that's how we get the change in temperature. And this all goes back to this drawing where we're computing the rate of change of temperature. And then we come across here, we have the same thing, and we come over, get our heat of reaction. We have this is an operational formula from above, and then eventually we can start tracking conversion. So the idea then is, that's already been done, is that you take this second operational row and then you copy it all the way down to the end of the table of volumes, which we showed was going down about 7,000 rows. This presents a fairly complicated calculation, which can take a little while to take a few seconds to update using the spreadsheet and the computer. Now, what we want to point out is that associated with this, we have a number of different defined functions in VBA to help carry out these calculations. And I mentioned one over here that was heat of reaction, where we're using a function called HTRxNP. All right, so we're using that. And so we need to see what are the VBA functions that go into this model. All right, so we can go over to the Visual Basic Editor. All right, and this is the model, this is the workbook that we're working with, and we have module 1 and we have module 11. And so for module 1, all right, what we're doing here is we're calculating the heat of reaction just temperature based, all right? And that's the formula that we showed, heat of reaction just based on temperature, not considering the contributions of pressure. And then we have a function here to calculate the heat capacities, all right, where we supply a component name, all right, and then the temperature, and it computes the heat capacity for that temperature using coefficients that we have determined from the NIST literature or documents. And then we have the heat of reaction, including the effect of pressure, all right? And that's more involved. And it involves using these tables that are back on the spreadsheet. And in this case, we're doing vertical lookups in these tables to find the appropriate values and plugging them into the calculations that correspond to those matrix calculations that I described in coming up with the mixture coefficients. And then we eventually get down to the point where we're able to get the heat of reaction, including pressure by doing the one with temperature, and then including the values for the pressure sensitive enthalpy with the appropriate stoichiometric coefficients. Okay? So that's what we have there, and that's what's necessary to solve this particular model. So if I come back over, all right, the model is always solved, and let me back off on the scale a little bit to 100%. The model is always solved, and here from the bottom of that very deep table, we bring up the final temperature in the reactor, which is 418, and this, I believe, is Celsius, not Kelvins. Sorry about that. And then the final conversion is 21.8%. And it's well known with ammonia that the conversion per pass is in the neighborhood of 22%. So we can then, having this, we can use specific columns of our solution, and we can create charts. So here is a chart of the molar flow rates as you go through the reactor, all right? And it shows that the reaction essentially shuts down when we get a little more than 6 cubic meters, and we've got our green here is the ammonia being produced, and we've got our hydrogen and our nitrogen being depleted, all right, as we go through that. And the hydrogen is on a much larger scale than the nitrogen, and that's why, although the curves look adjacent, they're really not in terms of scale, because you have, for the stoichiometry for NH3, you've got 3 times as much hydrogen as you do nitrogen. So, and then we can look at the temperature profile in the reactor, and it looks like this. And it starts at 270 Celsius and goes up to somewhere around 420 or a little bit below 420. And you can see how it sort of shuts down. And what's happening here, as you get to this temperature, the reverse reaction starts to play a more important role, and eventually the reverse reaction is balancing the forward reaction, so we get no further conversion. And then this is the conversion profile, a similar form. It starts at 0 and it ends up somewhere around 22%. So let's go back to the slides and just walk through this from the slides. And you also have, of course, the spreadsheet that you can work with. And so these are the blocks that correspond to the basic data. And you'll notice that some of these were, for instance, the heat capacity that was obtained by taking properties from HYSYS. It could also have been Aspen Plus or the Aspen Properties package, and then fitting polynomials to those statistically and coming up with these coefficients. We've got heat capacities, molar enthalpies, again taken from HYSYS properties, and we have our kinetics. And then we have the additional parameters needed for the Peng-Robinson equation of state. And this, we covered this, the binary interaction matrix, the Pitzer acentric factor, the omegas, the critical temperature and pressure, all right? And we've got, some of these are duplicated, like the critical temperature here and over here. And then we have our lengthy table, all right? And we went through all of that with you. And this slide shows some of the individual cells and how they're put together with the Euler method, and then the stoichiometry, the forward reaction rate, the rate of change of nitrogen, all right, flow, and then how we get the heat of reaction, and we have the Euler method being applied for integrating the temperature. And these are the charts, okay? So that's what that looks like. And then we take a look at the supporting VBA functions. This is where VBA comes into play, where we have our function that computes heat capacity, all right, given the component that we're looking for, and it reads values from that heat capacity table on the worksheet, and then it takes the temperature, converts it to kelvins, divides by 1,000, and uses the fourth order formula to compute the heat capacity for that component. And then we have our temperature-based heat of reaction, which again reads values from the spreadsheet, the basic data, and calculates the temperature-based heat of reaction. And then we have the lengthy one, which is including the pressure in the heat of reaction. And this repeats calculating the temperature-based heat of reaction. And then it has the somewhat lengthy calculation involving the Peng-Robinson equation of state and the equations that are used to develop the mixture coefficients for our calculations of the pressure-based function. And then there's the final down here, which combines the temperature only with the adjustments for pressure. So that is the VBA. And again, some of these calculations could have been worked out on the spreadsheet instead of using VBA, but in this case, VBA is a much more efficient way to approach this, okay? So let's move on and now do the final simulation for this model, which is the full model, all right? And here the information flow diagram is a little more complicated. The top end is very similar up here with our rates and solving the equation for nitrogen, stoichiometric relationships for hydrogen and ammonia, our total flow, and our calculation of partial pressures. But then the pressure here is no longer constant. So we have to obtain the pressure, and we do that by solving the differential air-gun equation here, and that provides us with the pressure, all right? And the pressure can then be used in these relationships up here. And then instead of solving a differential equation for the temperature, we have the enthalpy balance here, and we use the enthalpy balance to find the temperature by solving the nonlinear relationship here. This gives us the temperature. Down here we need the average molecular weight. We're able to get that with our flows, and we need, this is our Peng-Robinson equation of state that we solve in order to get the specific volume. That gets us the density with the average molecular weight, which we need for the differential air-gun equation. And then we also need the viscosity here. So what we do is we predict the dynamic viscosity from the intrinsic viscosity times the density. And the intrinsic viscosity is much more constant for the gases going through these changes. So we use that as a constant parameter. Okay, so that's what this model looks like. And then we formulate the solution of the model in the exact same way we did the simplified model. It just involves a little more complexity in the solution because we have to solve this for temperature as an algebraic relationship, and we have to solve this for specific volume as a nonlinear algebraic relationship. And we know how to do those kind of things, but we accomplish them in VBA. So what we'll do now is we'll come back to our spreadsheet, all right, and we'll close this spreadsheet. And we'll open a spreadsheet which is called Ammonia Simulation Full Model. And again, it's got a similar flavor and a similar layout in terms of our basic data. There are some new things there, such as our kinematic viscosity, all right, which is the Greek nu letter that we used. So we've got that information, all right? And then we've got our calculation of our mass flux. That is the capital G sub zero, which we use in the airgun equation. So we calculate that for the feed because it doesn't change going through the reactor. And then over here, we have some of the same information in terms of heat capacity coefficients and the Pitzer information, the binary interaction matrix, and the critical properties. So that's all very similar. And then what we're going to do is we're going to take a look at how the solution layout down here changes because of the way we're now solving the model. So let me again get our zoom up to make things a little more visible for you. And we'll come down here. And again, here, this is the initial. Much of this is the same as the last. These are the feed conditions, all right? And this is the feed pressure. But now we've got this as a column here because the pressure is going to change because we're solving the airgun equation to model that. The temperature is the same kind of relationship we had before. We've got then partial pressures, same as before. We've got our forward and reverse reaction rates, just as before, but now things change a little bit. Because here I've got the same derivative for my flow of nitrogen, all right, molar flow of nitrogen, but now I get into a block here to solve the airgun equation for pressure drop, and I need the average molecular weight, which you can see back here, this block, I need that. So that is a long formula for that. I need my density, all right, and the density is 1 over the specific volume, all right? And the specific volume, I'm getting that from the Peng-Robinson equation of state, all right? And you may wonder why this is delaying a little bit right now, and it's because it takes quite a while to compute the conditions on this spreadsheet. So be patient for a moment. We get our viscosity, all right. Once we know the density, we get the viscosity from the density and the intrinsic viscosity, which was up there. And then we have enough information to calculate the derivative of pressure with respect to distance with the airgun equation. And so we do that, and then we convert that over to pascals per cubic meter, just units change, and then atmospheres per cubic meter, again changing the pressure units, and that gives us what we need to solve for the pressure, all right? And so we'll see that in the next row. We come back here, and this is now a little bit different because we've got our heat of reaction as before. And then we have now a derivative of H with respect to V, and we have our H value, and then we use a function to find the temperature. And the function finding the temperature is implementing this calculation right here, okay? So we do that, and we've got our calculation of conversion. Now, if I come back over, it's very similar. Down here, this just implements the Euler method to compute and predict the next nitrogen, all right? And then the hydrogen, all of these are the same in terms of using stoichiometry, or the inerts just pass through without changing. We get our total, we get our pressure, and now the pressure becomes solving the Ergun equation for the next pressure using the Euler method, a very similar thing. And the temperature is just mapped here over from column A, B, so we'll get there. The partial pressures are what we had before as the reaction rates and the derivative of the flow of nitrogen, and then we've got our calculations for the Ergun equation, which are the same as before. And then we've got here the derivative for enthalpy and the enthalpy, and that again uses the Euler method to move the enthalpy along. And there is a function in Excel VBA called find T that we will look at, and the find T function is what solves this relationship for the temperature, okay? So that's what that looks like. Now if we go over to VBA, get the full model. The first module has the same relationships that we had before, all right? But then it has the find T function down here, and the find T function solves the enthalpy balance for the correct temperature. And it does this in a similar way to what we did back in Bootcamp 3, where it uses the variation on the Newton's method, which is called the modified secant method, in order to find the correct temperature, which balances the enthalpy to zero. And for that, it needs a function called FH, and that function is down here, which is essentially the balance on the enthalpies, where this is the enthalpy that is feed, and then we need to have all of the current enthalpies summed up be equal to that by putting in the correct temperature. And this finds the correct temperature, and it converges that, and then it returns that temperature over here to this particular cell, all right? So that is that part of VBA. And then the second part of VBA is the one that solves for the specific volume, and that is this part down here, all right? And so for the specific volume, it is just a series of code that goes through all of the calculations to come up with the M sub I, the A sub I, and the B sub I for the individual components. And then it computes the Q matrix here, all right? Computes the Q matrix. Then down here, it gets the mixture coefficients, all right? Gets the mixture coefficients. So it's got all of that information. And then what it does is it goes through, again, modified Newton's method or modified secant method in order to find the specific volume that satisfies the Peng-Robinson equation of state, which is down here, where we've got the pressure minus the right-hand side, which predicts the pressure, and so it modifies V until this goes to zero, and the Peng-Robinson equation of state is satisfied. So that's how that works, and it comes back here and calculates the specific volume, all right? And that is shown here for calculating the density, all right? The molecular weight average divided by the specific volume that we get by solving the Peng-Robinson equation of state, okay? Now, having done all that, solving it all the way down, again, 7,000 rows deep, we can plot the molar flow rates just as before, and they're a little bit different than the ones that we did with the simplified model, not dramatically. We have a temperature profile as before. It's a little bit lower than the other one. We have now we have a pressure profile because we have a pressure drop going through the packed bed, and you'll note it, this goes from 150 atmospheres down to about 144, all right? So that's about a 4% decrease in pressure, and you have to look at that and you'd have to say, is that enough difference in pressure that I want to go to this model, or do I just want to assume a constant pressure over the reactor? That would be a judgment call, and it's probably somewhere in a gray area with a 4% difference. If you're really concerned about the accuracy of the model prediction, you're probably going to want to stay with the full model. And then we have our conversion again, all right, our conversion curve, which looks similar to the one that we had before, but doesn't give quite the same value, okay? So that is, let's go back to our slides. Just reviewing the full model, this is pretty much the way it was before. And now we have the rest of the basic data, and we pointed out that we've got the kinematic viscosity here. That was new. And then the mass flux was new because those were needed for the Ergun equation. And the rest of the basic data is pretty much the same as the other model. And then we have our wide table that goes through, sets up the initialization row, goes to the next row, where necessary, uses the Euler method to move the variables along of nitrogen and pressure and enthalpy, and then it has all the other columns needed to carry out the solution, supplemented by the VBA. And this is very similar to what we showed you on the other slide, showing you some of the formulas, which you can always look at on the spreadsheet, but describing what the formulas are trying to accomplish. And you can see how that relates to the equations on the slides. And then we have our VBA routines, the find T routine to solve the enthalpy balance for the correct temperature, all right, using the modified secant method to drive the enthalpy balance to zero. And then we've got the specific volume function that solves the Peng-Robinson equation state for the specific volume and returns that here, and it needs to find the volume that drives the equation of state, pressure minus the equation of state equal to zero, okay? And then we have our charts, all right, that show, in this case, the temperature and the conversion, all right? And then we have the molar flow rates, and we have the pressure profile, okay? So that's what that looks like. And this brings us to the end of the modeling of the ammonia reactor. In the next screencast, we're going to move on to the modeling of a somewhat different reactor. It's a tubular reactor, but it's not packed bed, and it's not adiabatic, and it involves heat transfer. And it also presents us with a 2-point boundary value problem like we experienced, for example, with the heat exchanger in our Bootcamp 3. So we'll call it right now for this screencast, and we'll see you on the other side for the next reactor model.